Okay. So now we were talking about just delatch. Let's just look at a problem so that you understand the truth table, what is happening. So as we said, when enable is 0, what is happening is whatever your initial state is, you will have that as a state here. So now you have to ask yourself a question here. What is the initial state when enable is 0, right? So if it is 0, so that has to be given. If it is 1, then it would be 1, right? So there would be different output based on both, right? But when the enable becomes now 1, then you see what is happening. Now it reads the input. Now only you have to go to the input and you say, oh, input is 1. So what is going to happen when input is 1? You see your q is going to change here, right? The q changes. Now what is happening is, now let's say when enable goes to 0, what would happen? Again, the case is that your irrespective of what your d is, so it does not see what is happening to d, this remains 0 until your again enable comes. So then we can draw till the next enable, right? This is the retaining state, right? This is retaining. So that retains. Then what happens? Then the enable comes and then it sees, oh, output is 0, sorry, input is 0, input is 0, I have to make the output 0, right? It follows till 0. Then what happens? Enable again goes to 0, then it retains the output till the next enable comes, right? So this is again retaining. And then it retains, then it's again comes the input, then it sees, oh, output is again, your input is 1, so that it now latches into that input, then it remains until the next enable comes. It does not see anything, it remains 1, right? So this is again your retaining state, right? And then it sees enable, then it says, oh, output you have to be 0 because my input is 0. And then until now enable remains 1. So now the question is, what is happening is, when enable is remaining 1, whatever at the input you will see at the output, right? That is what is happening. So what we see here, if it was 0, then now you see if there was 1, it would start to just reflect on the output. Right now it would not retain because enable is 1, right? So these are simple timing diagrams which can give you this understanding of what is happening. So that is what I think I would suggest you to just draw these timing diagrams, and you will, I think, practice, okay, what is happening in the truth table. So that is the basis of a simple latch, which is what we know as the D latch here, right, in this case. Now what is the problem with this? The problem is this guy, right? So when enable is 1, you see that you are getting, this is behaving like a transparent, right? There is no retaining. That means in case if this enable was 1 and there was some noise or some kind of misbehavior of the input was happening, right? That means like debouncing, we saw one of the case. Still, this is a problem because then enable has to deal with that, right? Enable has to go 0 so that that debouncing does not happen. But within the operation, if it happens somewhere, then I have to make the enable 0 and all of that I have to do. The question is, and that has to be done with the new control circuitry where this has to be done, that E has to go 0, right? In that control circuitry. Question is there a better way to deal with it in R with the understanding of the latches which I have? Right, the goal is very simple for me, and the problem is also, yeah, I mean, it's very well defined here from here also, that wherever the enable is there, whatever your noise, if your input is oscillating, right, this is passed to the output also because it's transparent, right? Now the question we are saying is, oh, it does not need to. What my requirement is that I need to have some way so that it can only know the input, let's say at the some instance where I am, my enable is going 1 or 0, right? For example, it does not, whenever the enable is 1, it does not need to be transparent in for the whole duration. It only reads whenever my enable goes to 1 or 0, and then requirement is the input is read only at only when your enable goes from from 0 to 1 or 1 to 0, right? That is what I want. So that means rather than a latch which is open for the whole enable cycle, I want to only latch onto the edge of the enable, right? Edge of the enable. So these are the device, or the latch is what is we call is the label sensitive, right? Because till the time you see your enable is 1, you are able to pass whatever is there at the output, at the input, right? Because that is the, it depends on the level of the input. But here what we are running into the problem, we are saying rather than the label, we will only define the edge, and that is why these devices are called edge sensitive or edge triggered, right? So that is what we want to design with this kind of device. And to do that, now you will see that only one trick is needed to do that. Because what is happening is when you are passing this, the enable, whenever it is going 1, you are reading the data. But suppose if I could do, which is what I could do by using two different kind of latches, where what is happening is there, one is the active high enable. That means the enable we are getting at when enable is 0, there is no change happening. But in the active low, when there is a bar, right, of the enable, that means there is an inverter connected. But basically that is what it would mean, right? So whatever you are getting, there is an inverter connected, right, to the same enable what you are getting here, right? That is the meaning of this bar is. So then what we see is that whenever this is there, so we will just know that it's opposite table, right? So that means, yeah, here en whatever is active low, so it means when it is 0, then we know that the output is 0. When it is enable is 0 or input is 1, the output is 1. And when enable is 1, that is the same case as the active high there, and then whatever the input is, this output remains no change, right? So it's just opposite of that table, right? That is what happened because there is an inverter connected, or which is what we know as the also the active low signal, right? Active low means whenever this is low, then only it is active. Whenever it is 1, then it is not active, right? That is what it simply means. It's just the opposite. Now the question is that using these two different kind of enable, because one is enabling when en is 0, right? Sorry, en is 1, this is the active high. When en is 0, this is enabling. So now by combining this, is there a possibility that I can design an edge triggered or edge sensitive device, right? And that is what we do in the next solution. We combine them. Combine in the sense, we know, so this active low is, it can be seen as, let me just draw so that if you don't want to draw this inverter, you can think of it as a, this is active high, just that there's a, this is another interpretation, or let's say, let me draw the interpretation. So basically what we are saying is your D is there, very good. This is Q1 bar, right? This is your D which is coming. You have a clock which is going into E, which is your enable signal, right? And now what you do is, instead of this D is passed here, okay, good. And then Q, this is Q2 bar or Q bar, let's say. In this case it is written because that is what is looked like. And then this E, which is what is there, is uh, coming from a inverter. So that is what is changing, okay? And now for this we need to know what is going to happen. And your clock or your enable signal looks like this, right? This is given as a clock, which is your, let's say, an oscillating signal like this, what is given. Now let's see what happens, right? That is what is happening in each. So when, let's say, clock is 0 or enable is 0, what is going to happen? Let's see, right? So when enable is 0 here, then we know that this retains the state, right? Whatever the Q0 was, or Q, right, Q0 was, will be retained here. When Q0 is retained, now let's see what is the state of the second one. So when clock is 0, you see enable is 1 here, right? So when enable is 1, that means it would pass whatever the previous state of the first circuit was, right? Whatever the previous state of the first circuit was, it would just pass that to the output, right? So what is that state? So that you have to assume something. Let's say Q0 was 0 initially, right? So if it was 0, then Q1 we know is going to be 0, right? Because it just remains at 0, right? Enable is 0, so it retains that state. Here, Q, if it was not 0, right? Because this is going to pass, you will see that this will pass this Q equal to D, right? This becomes Q0. Okay, and this is Q0. Now, next is what is going to happen. That is interesting. So now the edge comes. Edge comes when clock edge becomes, or the clock becomes to 1. Now you see this guy will go to 0, and this guy from 1, it would go to 1, from 0 to 1, right? So let me write 0, right? So now what is going to happen when this goes to 1? Suddenly now it starts to see the data, right? So, and you see that D is, what is D is 0. So Q0, though it is transparent, but still it retains that, right? So this is when Q1 becomes D, right? Because it is 0, it sees 0. Now what is happening to the next one? Next is nothing, because its enable is 0, so it does not see the data at all. So Q is, what is happening is Q is, what is Q doing? Q is retaining. Q is retaining, right? Because it just retains. This is the retaining part. That is the different here, because it's not passed like how it is passed in the first latch. You see second latch is just retaining, it is not passing. So Q, you don't see the D yet, right? Now your, let's say, clock becomes 0, right? So when your clock becomes 0, what is happening? When your clock becomes 0, this becomes 1. So when it becomes 0, now you see your D is now again going into the retaining mode, right? So Q1 will continue, right? When your clock is 0, right? So it continues till here, because it does not see D at all, right? It just retains. This is the retaining mode it is in, right? Let's call it retaining, right? So now what is happening to the output? Output is, because it has said, okay, you have already got the D, give it to me now, because I am going 1. So that means I'm going to pass whatever D you have seen. And what is the D it has seen? It has seen 0. So then you will see that this cycle, this becomes D, whatever that D was, which I retained. Okay. Let's take a simpler problem. I think this is little complicated in a sense that there are multiple transition. This you can do on your own, but let me do a simple problem which we can better appreciate. Okay. Just 2 cycles, I think, should be fine. So a simpler problem would be where I am changing, or I'm making few transitions. So let's say what I'm making is D is like this, right? For example, and my clock is, for example, like this, right? Right, and this is different. So this, right. So this is your clock. Okay, this period is same for clock, but this is the clock. Okay, so now when we see this clock, let's see the what is happening to D, right? This is your D. So we drew Q1, and another output we have to draw is your Q, right? So when Q1 we are drawing, we said initially, if we assume this thing, when clock is 0, it retains. So that means whatever your Q0 was, it would just give you Q0, right? That is what the station. And the same thing, you see that when the E was, or clock was 0, this signal for the second latch would be 1. So that means it would pass just whatever was there, right? So this is the passing state. So that means D is equal to, or Q is equal to Q, right? This is retaining, this is pass, right? That is what is happening in 2. Now when clock remains 0, what you see is this is the same situation will remain, right? So now whenever this is there, this will continue, right? This would retain, because clock is 0. clock is 0 means the first latch is just retaining, right? This whole thing is retaining, right? Now let's see the what is the happening to the second one. The second one, you see, it's though there is change in D, but it's not able to pass that change because your first latch has not seen the D yet, right? It has not passed the D yet. So what is the situation of the second latch is also just going to pass whatever it was passing from the previous pass Q naught, right? It was just passing the previous output of the first latch. It is just passing the previous output. So you see that though the D is changing, but it is not reflecting here, not reflected at Q because first latch of because Q1 does not change, right? And Q1, why is it not changing? Because the latch is not enabled yet. Now let's see what happens when you make it clock is 1. So when is 1, then what happens is now your D1, right? It starts to see what is D, and suddenly it sees, oh, D is 1. Oh, I have to make Q1, right? So that is the thing it would do, right? So then your Q1 become equal to 1, right? And when till when does it continue? It continues till here, right? Okay. And now what happens is in this period when Q became 1, what is happening to the second? Let's see the second, right? So second, now what is the mode it goes into? Because second enable now becomes 0, so it goes into the retaining state, right? It's just into the retaining. It's retaining the past, right? Retaining means that it's going to now see that, okay, if your Q, uh, your clock, which was now 0, right? When it became 1, then D became, or the Q1 became 1, but it is not, because it is in the retaining state, it is not able to yet see what Q1 has changed. And when does it see that happening? Yeah, this I've already written, retaining, right? Because it's retaining the previous state. It has not yet seen, because enable went to 0 there, so it is just in the retaining state. Now when the clock comes back, right? This is the period. Let me draw with the red line, right? So then when clock comes back, which is this part, what it happens? Let's see that what happens. So when clock comes back, or enable becomes 0, this guy will go into retaining, right? Retaining means it's just going to retain whatever your input is, right? That is what effectively this will do, the first latch. What is happening the second one? That is interesting. So second one, because now it saw that, oh, Q1 has become 1, now it would go, oh, I have to change also, and it would change it to 1. And that is when happening only at the edge. You see, it's happening at the edge. It is not happening throughout the period, only at the edge. You see, now your D1, whatever your 1 was, it is seen to the output, right? That is what is the interesting aspect here, right? Because it is seen, what was just before the edge is seen at the output, okay? And D was 1 before the edge, which is what is seen at the output because your Q1 was 1. And what happens? This does it continue? Yes, it continues because it starts retaining. This is the retaining state of the previous one. But the other one is passing, right? And it is passing 1 because it is seeing 1. Then the Q again becomes, clock becomes 0, sorry, 1. Then again you see that this will start passing, right? The first latch. And it starts passing. Here it is passing, but what is happening now? It's going to, as soon as your clock becomes 1, the other latch, the second latch, will go into the retaining state. Retaining means it's going to retain this, right? This is the retaining. And this retaining happen, and then suddenly you see that this clock goes to 0. Now what is going to happen is, this guy says, oh, this is the clock at which you are going to make a decision. Just let's look at what is happening before this. Oh, so there is a change happening, sorry. We just didn't take. Yeah, so this will go to, so because you see it was passing till here, but suddenly we saw that this input is becoming 0, right? This input is becoming 0, but you see what is happening at the enable, it is passing. So passing means this will become also 0 at this point, right? So when it becomes 0, now do you think that this will keep retaining till that point? Because it is retaining because it is off. But what is happening? Now, as soon as the clock goes to 0, that means second latch is acting. Now it is start to pass whatever it has seen previously. And it has seen 0 previously because this is 0, right? So when it is 0, it goes to 0. Again, Q1 becomes 0. And that is why you see that only whatever I am seeing here, the data at the queue, I am seeing that it is only collected at edge, right? It is just collected before the edge. Just before the edge, what is my input is collected. And that is why we call this device as edge trigger device, right? Edge triggered device or element, right? And this is what can be represented also very simply as a D flip-flop. So rather than now enable, because we know we just draw a triangle, so that this differentiates a latch from a flip-flop. So that means when you draw this kind of thing, one knows, okay, you are talking about this edge triggered devices, right? So that which is triggering only at the edge, right? So let's, yeah, I mean, this is what one can draw. You can see what we were trying to draw, right? There, retaining. Just that it was a lot of instances were there. So this is something you can do on your own. But now, suppose if I was having opposite combination, then obviously this would become opposite to that, right? So let me see. This was where we see the thing which was happening at the negative edge of the clock. So that is why it is shown as negative edge is shown as the opposite or circle of that, right? Because you know there is just an active low, right? Because clock when it goes from 1 to 0, then only you see that the output is latching or it's getting the whatever is the input, right? That is what the case of the flip flop is. Now you are just considering an opposite case. So this is the case which we have seen where you can draw this as clock. It means that transition or uh, flip flop, this is called flip flop, which is the edge trigger device, sees the input just before or passes, not sees, let's say passes the input, or just before the clock transition from 1 to 0, which is also known as negative edge of the or at negative edge of the clock. So that is the basic thing which is happening here, that because clock was, we saw from the operation itself, when clock was going negative, then this was able to pass, which is what we can see from here also, that see when negative going, you see D is 0, its pass is 0. Okay, so let's just look at Q1, Q, sorry, right? Because we have described this with Q now, so there's no need for looking at Q1. So when negative edge D is 0, oh, Q is 0, very good. It waits till the next negative edge. Next negative edge, D become 1, okay, it becomes 1. That is the thing. You have to just look at the negative edges. Then you see next negative edge, oh, input is 0, let's make it 0, right? This becomes again 0. Next negative edge, wait, oh, input is becoming 1, let's make it 1, right? Next negative edge, okay, input is becoming 1, let's keep it 1. Next negative edge, okay, input is becoming 0, let's make it 0, right? That is how. So it's only happening at negative edges that it registers the input. But we have seen the details of it, why it is happening. It's just two latches which are uh, basically enabled by two different, sorry, two enabled signals which are of opposite polarity, right? In the sense that one is active low and one is active high signals here, which we see in this. So that is what is the D flip flop. Then obviously you know that rather than having this a negative edge, there is a possibility of doing it the positive edge. So this is a sensitive name. Let's not use master slave, but you know this is a D flip flop we are using talking about, right? So that means opposite combination. You see that when uh, so whatever is the for the second stage or the second latch the going that is what defining the clock. So this is the flip flop which I'm drawing, right? This looks like this. So now things will happen. Clock positive edge, right? So which would mean the positive edge triggered flip flop, right? That is the name of this. Let's not draw Q1 that you can draw. May I can just easily draw the positive edges and register the output at the positive edges. You are welcome to do that for the whole circuit also if you want, but let's just do the for. So positive edges, D is 0, very good. At 0 it passes 0 initially. uh, what is the input q remains. Obviously you know that if the clock is not there, whatever the initial condition was, it would remain there, but here it says 0, so then it continues to be 0, right? This is because if it was 0 initially, then it continues 0, and then here it registers, it sees 0, it waits till next positive clock, it still sees 0, and now it will retain this thing till the next positive and see, oh, it has turned 1, so it would turn 1. Then it goes back again. Then it sees, oh yeah, it is now 0, I have to go to 0. Then it sees, oh, I have to go to 1. Then it sees, oh, I have to stay 1 till the next edge where I have to go to 0, right? So that would be your Q if you were to make it using the simple positive edge trigger. So this is, you can do the way which we did here also, right? The passing, retaining. But once you know that this is what is happening internally, then you can easily simplify it just looking at the data at the positive edge. That just before the positive edge, what was the input it would register and it would pass to the output, right? That is what you are looking at. Okay. So I think that is what is the observation for the master slabs. So you can see that we have already talked about these two edge triggered elements, right? And yeah, and this is very simply saying when the clock is positive edge, so going from 0 to 1, then it registers the input, right? So your Q and Q bar becomes 0 and 1, right? Suppose whatever, it just passes the input, right? And similarly here, when the clock goes from 1 to 0, then it passes the input to the output, right? So that is what is happening in the two D flip flops. Okay, so now we will go further with this circuit and see what else is there for. So that is in the next bit of this video. Okay.